Hello, everyone. Welcome to Physics 213. This is Lab 4, which is going to be on basic studies in electricity. And we're going to be talking about two different topics. So the first topic is going to be electrostatics. Basically, we're going to be computing the electric field due to point charges. And I'll explain the background on that in a minute. And then the second part is going to be on circuit analysis, basic circuit analysis. So actually, I've already recorded a video last year on the basic circuit analysis. So it'll be the same. You can watch the same video. Last year it was labeled Lab 9. This year it'll be like 4B. It'll be the second part of Lab 4. Okay. All right. So to start, let's go over a little bit about electric fields. So I'm going to switch over to the iPad. Okay, so we want to first discuss electric fields due to point charges. Oops. Okay, so let's say I have a positive charge. So I'll just represent that by a red circle here. So this is my positive charge. Now, any object that has charge is going to create an electric field. In this case, if you have a point charge, it's going to create an electric field that points radially. So it's either going to be away from the charge or towards the charge, right, in the radial direction. And actually, if it's a positive charge, the electric field will be pointing away from the charge. So if I pick some points, let's say a point right here, maybe a point right here. And I look at the electric field, it's going to be, again, radially. So in this case, it would point something like that. Here, we're going to find out in a second that it depends on how far the location is away from the point charge. It'll be smaller electric field, so the magnitude will be less, so maybe something like this. If this is the same radius away up here, that would be the same length. So maybe something like this would be the electric field. If it were, let's say this is also the same radius, then this would be that electric field. The length of it, the magnitude would be exactly the same. Same thing here. So it points radially away from the positive charge. Okay, and of course we could have some, I'm only drawing a few of these, right? Obviously, you can have electric field at all points in space around that particular point charge. Okay, so if this is the charge Q, let's say we want to calculate the electric field right there. This is the distance from the charge to the location at which we want to compute the electric field. I'll call that R. Then it turns out to find the magnitude of the electric field, we already know the direction, right? The direction is going to be radial. So it'll be away from the positive charge or towards a negative charge. But to find the magnitude, like the length of those vectors, those electric field vectors, then you want to use the following formula. So I'll write this as magnitude of electric field due to a point charge. So it turns out it depends on several things. I'll call that E for the magnitude of electric field. There's a constant. This is called the electrostatic constant or Coulomb's constant, K. I'll explain what that is in a second. Then we have the charge itself, and it could be positive or negative. If we just want the magnitude of electric field, I'll just write this as the absolute value of the charge. right? So we'll just make it non-negative, and then divided by that distance squared, right? The radius, think of it, r as being the radius, the distance from the point charge to the location at which you want to measure the electric field. And the units for the electric field are going to be volts per meter, or this is equivalent to saying newtons per coulomb. The electric field is really the force. If you had another charge at that location, it'd be the force that the central charge exerts on the other charge divided by the charge itself. Right? So it's a force per charge is another way of thinking about the electric field. Okay, so again, let me write out what these things represent. So Q is the charge in coulombs. K is the electrostatic constant. And its value is approximately 9 times 10 to the 9th. And then the units are Newton times meters squared over coulomb squared. Right, but it's just a constant. It's around 9 times 10 to the 9th. And then R, again, is the distance in meters from the point charge to the location where you're measuring the field. So distance in meters from the point charge to the location where you are measuring the field. Again, think of it as like a radius, right? It's a radial distance. Okay, so here, let's actually do an example where we calculate the electric field at some particular position due to a point charge. So let's say I have, I'll go to a new page here. Let's say I have a positive charge, and let's say it has a value of positive 5 nanocoulombs. So the little n means nano, right? 10 to the negative 9th. So 5 times 10 to the negative 9th coulombs, right? 5 nanocoulombs. And I want to calculate the electric field at some location, let's say right here. And let's say that this distance from the charge to the location where I want to calculate the electric field is 4 meters. So in this case, that means R, right, is 4 meters. By the way, it's sometimes helpful to set up a coordinate system. Like if I call this, do this in green, let's say this is my X axis, and then my Y axis. So I put the point charge right at the origin, right? So this has coordinates 0, 0. And the place I want to measure the electric field at has coordinates 4, 0. Okay, so it means that that radius, that R, is equal to 4 meters. Okay, and I know that the electric field is going to look something like this. It's going to go outward, right, because it's a positive charge. And I want to figure out what that electric field is. Okay, so we know how to calculate the magnitude, right? The magnitude of the electric field is going to be K times the absolute value of the charge divided by R squared. So in this case, this will be 9 times 10 to the 9th. To save room, I'm not going to write all the units in there. And then the Q is, since it's 5 nanocoulombs, it's 5 times 10 to the negative ninth divided by, and then R is 4 meters, right, squared. And if you work that out, it turns out this is equal to 2.81. And again, it has units of volts per meter or Newton per coulomb. I think the simulation that we're going to look at later uses volts per meter, so I'm just going to leave it as volts per meter. And in this case, because we know based on our coordinate system, right, it's right along the positive x direction, then I could write this, I could write the vector as equal to the magnitude, and then it's in the I hat direction, right? Just none of that vector is in the j, it's all in the I hat, positive x direction. And again, this is like volts per meter. So that's really all you need to do to calculate the electric field. Okay, and again, if you had a negative charge, then the magnitude of the electric field will be the same as if you had a positive charge, but the direction is different. So now the direction will be pointing towards the negative, right? It'll be radially inward. In this case, so I'm closer here, so it'll be a larger magnitude, something like this. So it's going to be radially inward towards that negative charge. Okay, but the magnitude is exactly the same. It's K times absolute value of Q divided by R squared. All right, that's if you have a single charge, right, of some particular value. What if you have several charges and you want to calculate the electric field at a particular location due to those several charges? How do you do that? Well, this is where we have to use something called superposition. So let me explain this. So I'll say superposition. I have to spell it right. Superposition of electric fields. Okay, so this is the idea. To find the electric field, due to several charges, you find the electric field due to each charge. So you find the electric field to each charge individually. Then you add those electric fields together to get the total electric field. And remember, electric fields are vectors, right? So you have to add them vectorially. Okay, so here, let's do an example. Let's say we have, let's say I have a positive charge here. Actually, I'm going to call that, here, let me make a little coordinate system. Let's say that's 0, 0, just to make it easy. So this is my x-axis. This is my y-axis. So let's say this location of this positive charge is 0, 0. And let's say it has, I'll call it Q1. Let's say it has a magnitude of 2 Newton coulombs. Then let's say I have a negative charge, maybe here. And let's say its location is 0, -1. and let's say its magnitude, call it Q2, is -6 Newton coulombs. Okay, so basically what I'm saying is that the distance, right, from here to here is 1 meter, right, if it has coordinates 0, -1. And then let's say I want to calculate the electric field at some other location, maybe right here. And so this location I'll say is 4, 0. So that means this distance is 4 meters. Okay, so to do this, right, to calculate the electric field there, I would first have to find the electric field due to Q1, right? And remember, this positive charge is going to have electric field that points outward. And in this case, right, it'll be directly along the positive x-axis. So that'll look something like this. I'll call this E1. So that's the electric field due to Q1. And then the electric field due to Q2, right, which is that negative charge, first of all, it'll act along this radial line. And it'll be inward, right? And -6 is a little stronger, so it'll probably be a little bit longer. Let's say it looks something like this. So this would be E2. And then if I add them together, right, once I find E1 and E2, I add them together, that'll be the total electric field at that location due to those two charges. Okay, you could do this graphically, right? If I add these together, so if this is E1, and then I do tip to tail, so I move the tail of E2 to the tip of E1. Let's say it looks like this. Right, so this is E1, this is E2. Then my E total is going to be something that goes from the tail of E1 to the tip of E2. So it'll look something like this in this case. So we want to find that. We want to find the magnitude of E total and the direction of E total. Okay, so to do this, let's first find E1 and E2. Well, E1 is not too bad, right? To find E1, so remember that's the electric field due to charge 1. I can find its magnitude because we know it's going to be K times absolute value Q over R squared. Well, K, of course, is 9 times 10 to the 9th. The absolute value of Q is going to be 2 Newton coulombs, so that's 2 times 10 to the -9th. And the R here is this distance, right, which is 4. So this will be 4 squared. And if you work this out, it turns out it's around 1.1, I'll say 1.13, I'll round it, 1.13 volts per meter. So that means the vector E1, we know it points along the positive x direction. So the vector E1 is going to be 1.13 I hat, and then it'll be volts per meter. Okay, now we need to figure out E2. This is really, I should be careful here. Let me write Q1, and this is like R1 squared, right? Where Q1 was given 2 Newton coulombs, that's right here. And then R1 was 4 meters because that's this distance on top here. Okay, so to calculate the electric field due to charge 2, I need to know this distance, right? This is like R2. Well, notice here we have a right triangle. We know this distance is 1, right? This distance is 4. So I can figure out R2 here. It's simply going to be the square root of 1 squared plus 4 squared, right? Which is the square root of 17. So that's R2 meters, square root of 17. So that means the magnitude of E2 is going to be K times Q2 divided by R2 squared. So this will be 9 times 10 to the ninth times, I just want positive, right? So it'll be 6 times 10 to the negative ninth, because Q2 is negative 6 Newton coulombs, but we want absolute value, just want magnitude. And then divided by square root of 17 squared, which of course is just 17. If you work this out, you're going to find this is equal to around 3.18 volts per meter. Okay, so that's the magnitude of E2, right? That's the length of that particular vector. Now we need to figure out the direction. So really we need to figure out this angle here, right? This direction. So again, using basic trigonometry, let me go to another page. Remember, this length is 1 meter. This is 4. We're looking for this angle theta, right? So I know that the 1 is opposite the angle and the 4 is adjacent. So tangent is going to relate them together. So I know that tan theta must equal 1 divided by 4. And if I take the inverse tangent of both sides, then I'm going to get theta is equal to the inverse tangent of 1/4, which is around 14.04 degrees. Okay, so that's the angle that E2 makes with the negative x-axis. So basically it's the reference angle, right? So if I were to draw this out, let me draw out E2. Right, it's in the third quadrant. It looks something like this. We know that this angle is 14.04 degrees. This is my E2. And I really want to find its components, right? I want to write it in vector form. So in component form. So if I project onto the x-axis, this distance is E2x. If I project onto the y-axis, this is going to be E2y. So then if we extract out this little right triangle here, right, again, if this is 14.04 degrees, this is E2y, this is E2x, and this is the magnitude of E2, which we already know, right, the hypotenuse, then we can figure out the components, right? And in fact, because the x component is pointing to the left, it's got to be negative, and the y component is pointing down, it's got to be negative, right? So in this case, I can say that E2x is going to be negative the magnitude of E2 times cosine of 14.04 degrees. We know the magnitude of E2, right? That was 3.18 times cosine of 14.04 degrees. And that's around negative 3.08 volts per meter. And then E2y is going to be negative, because it's downward, E2 times sine of 14.04 degrees. So that'll be negative 3.18 times sine of 14.04 degrees. And I'm rounding a little bit here, but I'm going to get around negative 0.77 volts per meter. Okay, so basically I have E2, right? If I write E2 in component form in terms of I hat and j hat, then the vector E2 is going to be negative 3.08 I hat minus 0.77 j hat, right? Volts per meter. Which makes sense. It's in the third quadrant, right? Both components should be negative. So now, remember, ultimately the goal is to find the total electric field at that location. So to do that, I simply add E1 and E2 together, right? So E total is going to be E1 plus E2. Well, we know what E1 and E2 are, right? Remember, E1 was 1.13 I hat, and then E2 was negative 3.08 I hat minus 0.77 J hat. So if I combine the i's, combine the j's, there's only one j, don't have to really do much. Let me grab my calculator. In this case, this is going to be 1.13 minus 3.08. So it'll be negative 1.95 I hat. And then the j hats, there's only one, right? So negative 0.77 j hat. And again, this is volts per meter. So that's our electric field, right? It's in component form. Now we may also want it to find the magnitude and direction of that electric field, right? Put it in polar form. So we can do that fairly easily, right? I can find the magnitude by using Pythagorean theorem. Remember, it's just going to be the square root of the x component squared plus the y component squared. And if you work that out, it's going to be around 2.10 volts per meter. And then I could find the direction, right? I should draw a picture here. It looks like the total electric field is in the third quadrant, right? So I have around negative 1.95. So this is like my x component of E total. And then the y is like negative 0.77. So the total electric field is going to be something like this, right? In that third quadrant. So we found the magnitude, we found the length, it's 2.10. And then I could find this angle here, theta, right? The reference angle. So if I extract out that right triangle, in terms of distances, now this is just 0.77. This is 1.95. So I know that theta here is going to be inverse tangent of opposite over adjacent. And if you work that out, it's around 21.5 degrees. Okay, so we could say that the total electric field at that location due to those 2 point charges is equal to 2.10 volts per meter at, and we could say 21.5 degrees, but then we have to give it a little more information to determine the fact, to let people know that this vector is in the third quadrant. We could say 21.5 degrees south of west, so S of W. Or if you wanted to give just an angle by itself, you could give this angle, right, that goes from the positive x axis all the way to there, and then you just have to add 180, right? So that would be like, it'd be 180 plus 21.5, which is 201.5 degrees. So you could either say the total electric field is 2.10 volts per meter at 21.5 degrees south of west, or you could just give one particular angle and it's implied that it's measured from the positive x counterclockwise. Okay, so let's look at what you guys need to do for your lab report, for your group lab report for this lab. So let me go back to that handout. Okay, so in the first part, we have this set up. So we have a single positive charge at 0, 0. And then and these are just locations at which we want to measure the electric field at, okay? So question 1, you're told that this is a +1 Newton Coulomb charge. And I want you to calculate the magnitude of the electric field at this location, 1, 0, at 3, 0, at 0, 1, and at negative 2, 0. Okay, so you want to show all your calculations, just calculating the magnitude, and then you want to fill in the table here. So for those 4 locations, you want to calculate the magnitude of the electric field. All right, then we want to compare to what we would actually measure, and how we're going to do this. We're going to do it using a simulation. Right, so let me show you how the simulation works. We're going to set up this configuration. In fact, in this case, it's just one point charge, but 4 locations at which we want to measure the electric field. And I'll show you how to read all these values from the simulation. So let me go to the simulation. Okay, so here's the simulation. So what I would do, I would turn on the grid, right? So we can, and then if we place a charge at some location, if there's just a single charge, we can call that 0, 0, just to make things easy. So let me place this +1 charge at right in the center here, right around 0, 0. And notice what it does automatically is it shows you the electric field at each of these points, at several different points. And when it fades here, that just means the electric field is getting weaker and weaker. So it's stronger near the charge and weaker away from the charge. Okay, but we're not really going to need it. So I'm going to turn that. It's kind of fun to play with that, but let me turn that off for now. All right, so we want to place the sensors at those different locations. So let's say one of the locations was 2, 0, right? So I'm going to call this 0, 0. This charge is at 0, 0. It turns out, if you look at this grid line here, that if you go 2 of the large intervals here, that represents 1 meter. You could also measure it. You could use a tape measure here, put it at the charge in the center, and you could measure out 2 meters, right? If you want to go to 2, 0. But one of the, 2 of these large grid lines represents 1 meter, right? 100 centimeters. So we actually want to go to right here. Okay, it may not be exact, but as long as you're close, that'll be good enough. So you're going to put a sensor at that location. And then it shows you, right, the direction of the electric field due to that charge there. And if you want the value, so remember we want to compare what we get experimentally using the simulation to what we compute, you can just click on values here. So actually it gives you the angle too of the arrow. It says it's at 0 degrees and the magnitude is 2.24 volts per meter. If you have a 1 Newton Coulomb charge here, and we're measuring it at 2 meters away, right, from that charge. Okay, so you're just going to put the sensors at the different locations that were given in the handout. And you're going to you don't have to worry about the angles. You're just going to look at the magnitudes for now. Compare your computed values to what you measure here in the simulation. All right, so that's the first part. The next part, let me go back to the handout. So once you have your calculated values, and again, this is question 1, you want to show me all those calculations, how you got those magnitudes. Then you have your measured values from the simulation. I want you to compare them, right, by computing the percent experimental error. So compute the percent error for each of those 4 locations. All right, question 4. If you double the point charge to +2 Newton coulombs, predict how the magnitudes of the electric field at those 4 locations will change. And then you can simulate this by putting 2 +1 Newton Coulomb charges together. You just put one on top of the other one, and that represents +2 Newton Coulombs. And then you can measure it and see if it matches what you predicted. Okay, and then question 5. So instead of having a +2 Newton Coulomb charge at the center, replace it with 2 -1 Newton Coulomb charges. So that'll give you a total of -2 Newton Coulombs. So how do the magnitudes of electric field at those different locations compare to the values found in question 4? And then how do the directions compare if now you have a negative 2 Newton Coulomb charge at the center? Right, so you're just kind of playing with the simulation to answer those two questions. Okay, the next part, part B, here's where we're going to have several charges. So here's where the superposition of electric fields, where you have to add the electric field due to each charge individually. You add them all together, and that'll give you the total electric field. So here's the setup. You're going to have 2 Newton Coulomb, so positive 2 Newton Coulomb charge. Think of that at 0, 0. Then at 0, 2, so like 2 meters away above, you're going to have a 1 Newton Coulomb charge. And then at 2, 0, so 2 meters in this direction, you're going to have a negative 2 Newton Coulomb charge. Think of this as Q1. I label this Q1, Q2, Q3. And I want you to calculate the electric field at this location at 2, 2. So you have to find the electric field due to Q1. And so you're gonna have to figure out what this distance is, right? Because that'll be like the R. And we know it's gonna point like away. So it'll be something like this. Then the charge due to Q2, which will be towards Q2, will be down like this. And then charge due to, or sorry, electric field, right? Due to Q1, electric field due to Q2, which is down, electric field due to Q3, which is going to be in this direction. And you have to add those three electric fields together. Then I want you to go to the simulation. So question 6 is basically compute those values, right? Find the magnitude and direction of the electric field, the total electric field at 2, 2, which means you have to find the magnitude and direction of the electric field at each of the, due to each of these particular charges and add them all together. Then I want you to set this up in a simulation, measure the magnitude of electric field and the direction at that 0.22, and then compare what you got from what you computed. Okay, so that's basically question 7. You have the computed values, right? The magnitude and direction of that electric field. Then you have the measured value from the simulation, the magnitude and direction. And you want to compare them by computing the usual percent experimental error. Okay, so that'll take a little time, right, to actually do the calculation, because you have to do, again, you have to compute like 3 electric fields due to each of these charges and then add them all together to get the total electric field at that location 2, 2. Okay, and then the last thing I want you to do for this first part of the lab is question 8 here. So let's say you're given this configuration, a positive 3 Newton Coulomb charge at 0, 0, and then a positive 1 Newton Coulomb charge at 4, 0, right? So 4 meters away. Now, if you think about this, right? Remember, the electric field due to this charge at 0, 0 is going to be directed to the positive x direction, right? And it'll be pretty large because you have a plus 3 Newton Coulomb charge there. And an electric field due to this positive charge, the 1 Newton Coulomb charge at 4, 0, if you're to the left of it, it's going to be pointing to the left, right? Because it points outward, radially away from the charge of its positive charge. So if you, there must be some location here, right? Between, you can think about this, see if you can understand this argument, somewhere between these two charges where the electric field is 0. Because the electric field due to Q1 plus the electric field due to Q2 are going to exactly cancel out, right? And they're going to be 0. In fact, it'll be closer to this charge, right? Because this is a larger charge here. So it'll be closer to Q2. It'll be somewhere in here, some location. The electric field is exactly 0. Because E1 plus E2 will give you exactly 0. So I want you guys to find that location. Find where the electric field is 0. Give me the coordinates where the electric field would be 0. Okay, so that one you have to think about a little bit. You're gonna have to solve this. Show me your calculations, and then just give me the coordinates in this table here. Okay, so that's it for the first part. So we just did a little bit with electric fields due to static charges. The next part of the lab is going to be circuit analysis. And again, I've already created a video. I did this last year at the beginning of the pandemic. So then it was called Lab 9, I believe. So don't get confused by the number. It's going to be the same exact lab. So you want to watch that second video, and that will explain everything about the circuit analysis stuff that we need to do for the second part of this lab. All right, great.